A supernova is one of the most powerful and destructive events in the universe, a cataclysmic explosion that occurs when a star reaches the end of its life. It's like a cosmic death scream, a last and violent outburst of energy that can outshine entire galaxies for brief periods. Supernovae are rare, but when they happen, they mark the final moments of a star's existence, and the aftermath can be as haunting as the explosion itself. But how does a supernova actually explode? To understand this, we first need to understand how stars live and die. Let's break it down step by step, moving from the slow burn of a star's life to its final moments of catastrophic collapse. The life of a star, fueling the beast. Stars are essentially massive nuclear furnaces. They burn because of a process called nuclear fusion. Inside a star, hydrogen atoms are smashed together under extreme temperatures and pressures to form helium. This fusion process releases an enormous amount of energy, which is what makes stars shine. The energy also creates pressure that pushes outward, counteracting the star's own gravity, which tries to collapse the star inward. In a delicate balance, the outward pressure from the energy of fusion and the inward pull of gravity keep the star stable for millions, sometimes billions, of years. This is the phase of the star's life we're most familiar with. It's stable, burning steadily and shining brightly in the night sky. However, a star can't burn forever. Eventually, it starts to run out of fuel. When that happens, the star faces a terrifying fate. The beginning of the end, fuel depletion. For smaller stars like our Sun, their death is relatively peaceful. They swell into red giants and eventually shed their outer layers to become white dwarfs. But for stars much larger than the Sun, those at least 8 times more massive, the ending is far more violent. These stars are destined for a supernova. As these massive stars begin to run out of hydrogen, they start fusing heavier elements like helium, carbon, oxygen, neon, silicon, and eventually iron. Each new element fuses in layers, much like the layers of an onion. But the fusion of heavier elements doesn't last long. Each new stage burns quicker than the last. Once the star starts producing iron in its core, the end is near. Iron is a death sentence for a star because it doesn't release energy when it fuses. Unlike hydrogen or helium, fusing iron requires energy rather than producing it. This is the critical moment in the life of a massive star. The core collapse, death of the heart. As the core of the star fills with iron, it becomes unstable. With no more fusion to provide outward pressure, the balance between gravity and the energy pushing outward collapses. The star's own gravity begins to take over, and within seconds, the core starts collapsing inward under its immense weight. This is where things get incredibly dark, both figuratively and literally. The collapse of the core happens with terrifying speed, in some cases shrinking from a mass of thousands of kilometers across to a sphere no larger than about 10 to 20 kilometers. As the core collapses, the density becomes unimaginable and the temperature skyrockets, reaching billions of degrees. This implosion doesn't go unnoticed by the rest of the star. The outer layers, which have been held up by the pressure from the core, suddenly find themselves free-falling inward. As the outer layers collapse, they smash into the core. This violent collision is the spark that triggers the supernova explosion. The explosion? A violent outburst. The core collapse happens so fast that it creates a shock wave, which is a powerful burst of energy that races outward from the core. At first, the shock wave gets slowed down as it moves through the dense material of the star. But then something truly terrifying happens. Neutrinos, nearly massless subatomic particles, are created in the collapsing core and are blasted out in all directions. In an instant, these neutrinos flood the star's outer layers. Though they barely interact with matter, the sheer number of neutrinos gives the shock wave an incredible amount of energy. This causes the shock wave to speed up again, ripping through the outer layers of the star with immense force. The star's outer layers are blasted into space at speeds of thousands of kilometers per second. This is the moment we see from Earth, the light from the supernova as the star tears itself apart. For a few days or weeks, the exploding star can outshine an entire galaxy, making it one of the brightest objects in the universe. This moment of extreme brightness is the death cry of the star. The supernova releases more energy in a few seconds than our Sun will in its entire 10 billion-year lifespan. What was once a stable star is now a swirling cloud of debris expanding outward into the cosmos. The aftermath, what remains? The remains of the star depend on its original mass. After the outer layers have been blasted away, what's left behind is the core, which has collapsed into either a neutron star or a black hole. Neutron star. If the star was around 8 to 20 times the mass of the Sun, the core collapses into a neutron star. Neutron stars are among the most extreme objects in the universe. They are incredibly dense, so dense that a single teaspoon of neutron star material would weigh about as much as a mountain on Earth. They're also highly magnetized and can rotate at incredible speeds, sometimes hundreds of times per second. These rapidly rotating neutron stars are called pulsars, and they send out beams of radiation like cosmic lighthouses. Black hole. If the star was even more massive, the core collapses into a black hole, an object so dense that not even light can escape its gravitational pull. Black holes are the ultimate cosmic voids, regions where space and time are so distorted that the laws of physics, as we know them, break down. Inside a black hole, the star's mass is compressed into an infinitely small point called a singularity, and the event horizon, the boundary around the black hole, is a one-way trip to oblivion. Once something crosses the event horizon, it can never escape. The supernova's role in the universe, creation through destruction. Though supernovae are incredibly destructive, they are also essential for life as we know it. The explosion of a supernova sends heavier elements like carbon, oxygen, and iron, created during the star's life, out into space. These elements become part of the dust and gas clouds that form new stars, planets, and even life. In a way, we owe our existence to supernova. The iron in your blood, the calcium in your bones, and the carbon in your cells were all forged in the heart of a dying star billions of years ago. Supernovae are nature's way of recycling matter, taking the death of one star and using it to build new worlds. A dark reminder of cosmic mortality. Supernovae are both a spectacular and haunting reminder of the life cycles of stars. They are the universe's ultimate display of power, where the final death throes of a star create both destruction and renewal. The dark energy unleashed during these cosmic detonations reshapes the galaxies, creating nebula and star-forming regions. For humans, supernovae may seem distant and removed from our everyday lives, but they're a stark reminder of the vast forces at play in the universe. As we look to the stars, it's sobering to realize that they too are mortal. They live, they burn, and in the end, they die in a blaze of glory that can be seen across the cosmos. One day, billions of years from now, even our own sun will die, though not in a supernova, but in a quieter, more peaceful manner. Yet the remnants of other stars, their bones scattered throughout space in the form of elements, will continue to shape the universe, including the future of our own planet. Supernovae are not just the violent deaths of stars, they are also the birthplaces of new worlds. The dark chaos they create is necessary for life to continue elsewhere, reminding us that even in destruction, there is creation.